So, welcome back to the lecture series on machine learning. In the last session, we started supervised machine learning algorithms, where we specifically talked about linear models, linear regression specifically, and we also covered logistic regression. So, we will further talk about more supervised learning algorithms in this session. We would specifically talk about that why do we need more algorithms, why linear models actually fail. We would talk about decision tree, which is considered to be one of the important algorithms. We would also touch upon naive Bayes algorithm. We would also talk about ensemble based algorithms. And then we would be summing up by covering some important concepts in machine learning. To start with, why actually we do need more algorithms? It is an important question. So, if linear regression and suppose logistic regression that we covered in the previous session, if they worked everywhere, then obviously machine learning would have ended 30 years back, but it didn't, isn't it? Because the world doesn't behave in one single way, right? So, every algorithm actually secretly assumes something about the world, each and every algorithm, right? Linear regression, for example, assumes straight line relationships, as we saw. Logistic regression, on the other hand, assumes the clean separations. For example, KNN assumes that the similar things behave similarly. So, whenever these assumptions break, actually the new algorithm or these algorithms actually break, and therefore, there is a need of a new algorithm. So, let us take an analogy where teaching different students, for example, in a class. So, imagine that you are teaching all the students using the same method. So, same students, some students may learn by logic, some other students may learn by examples, some students would like to learn by repetition mode, some by visual thinking. So, good teachers adapt, isn't it? So, machine learning does the same thing with algorithms. So, algorithms are nothing but the teaching styles for data, I would say. So, why linear models fail first? Let us understand that, because they work well when the trends are smooth, when the noise is limited and when the relationships were simple, right. But all the real world is quite messy in nature. For example, stock market, you talk about customer behavior, you talk about medical data. So, when the data bends, the linear model also breaks, right. So, the real world problem is not, or the real problem is not the size of the data, but the real problem is the interaction among the data, right. So, real world in fact can be thought about as many factors acting together on the data. So, problems do not become hard because we add more features to it, rather they become hard because features start talking to each other, because there are so many interactions among the data, and that makes the things little complex. So, in a way complexity increases, the data surface also bends, right. So, let us talk about why a new algorithm would appear. So, every time the world adds a new twist or a new concept or a new feature, right. So, we invent a new way to capture it. So, real world is nothing but many factors acting together. So, the problems do not become hard, I told you, we add more features because of it. They become hard because the features start talking to each other, and that is the key concept of, or the reason why we are having so many algorithms. So, as the complexity increases, the data surface bends. So, let us first start talking about one of the very important algorithms, supervised learning algorithm, which is called decision trees. So, decision trees is like teaching the machines to think like the humans does, the way humans solves a problem, right. So, when a humans make a complex decision, so we do not calculate the formulas and all those things, we ask questions rather in order to get a solution. For example, a doctor may say that, do you have a fever? So, that question actually helps him to go beyond or towards a solution. A banker might ask like, is the income stable, right. Interviewer might ask that, can you explain your project. So, these questioning thought process enables us to lead towards the solutions. So, similarly, the decision trees exist because humans solve the problem by structured questioning. That is the key aspect of decision trees. So, a decision tree is nothing but, I would say, a sequence of intelligent questions where each answer decides the next question, and that series of question answer would lead to a solution, right. So, key idea over here is every question would split the world. Here the world means the search space, here the world means the actual problem space, right, and each split would reduce the confusion. So, the series of questions would keep on reducing the confusion till we get an answer or we are able to solve a problem, or maybe we are not able to solve a problem, right. So, final decision happens when the confusion is low enough or there is no confusion at all. So, in a way, decision tree converts this uncertainty into clarity step by step, not in a single step. So, by asking those series of questions, you are actually moving from uncertainty to a certainty level, and the certainty over here means a solution to a given problem. So, real world scenario can be, for example, medical diagnosis, right. A patient walks in to a doctor, and doctor may ask like, do you have a fever? If yes, that is a question that he has asked. If he says yes, or if he finds that yes, he would check the infections. If it finds that no, then it might check the allergy or the stress. So, the next question could be like, do you have a cough? Other question could be like, do you have a chest pain, right. So, each question actually is eliminating the possibilities. So, uncertainty to level of certainty, right. So, as I told you, decision tree learns this questioning strategy from past patient data, and if it learns to handle this question strategy, then it can solve a problem the way human does. As you can see in decision tree, how actually it looks like a decision tree. So, you would find it as a tree like structure. You would have some internal nodes and you have some leaf nodes over here. So, each internal node is when you are asking a question, and a leaf node is when you reach to a particular decision. So, you can have multiple decisions in a given problem, right. So, that is what, and each path over here which you see from, say, suppose any of the path to direction that you are seeing. So, it is nothing but the explanation of why that decision actually happened, right. As you can see at the root level, the entire problem would appear with you, right, and with every split would reduce the confusion, would increase the POT level, or would reach towards the certainty level. So, how does the tree learns? So, tree always asks the question, as I told you, that gives the clearest separation, and after the question data becomes less mixed or less noisy or more clearer, and the classes become more distinguishable. That is what I wanted to do. I wanted to reach to a specific class, right. So, the best question is the one that reduces the confusion the most, and that is how the overall idea is that in minimum number of questions, if you can reach to a solution, if I can reach to a decision, that is the overall aim of decision trees. So, at the beginning what would happen is all your data is mixed with a lot of confusion and you do not have any solution to it. I would call it as a mixed data, and it has different classes, different behaviors, different, and overall total confusion is over there. So, that mixed data would start at the root level. We would call that root is the entire data set or that data that we have, and the goal is what? To keep splitting the data until there is no confusion remains, and that is what I told you in the example, that we would keep starting from the root, keep on splitting the data till we reach to a decision where we would end at a leaf nodes, and there can be multiple decisions. Again the same thing which I told over here. As you can see that for starting from the root, you might ask a question, it can be broken into left and right side with yes and no, then again you would ask some series of questions, ultimately you can reach towards the leaf node, right. So, let us understand when this decision tree would work the best. As I told you previously also, every algorithm works better in different scenarios, right. So, in some circumstances one of the algorithm might be a better choice as respect to the others. So, sometimes the most important question is not is the model accuracy or how accurate that model is, right. So, in fact, what is important is I can't explain this decision to a human, right. So, can I explain the decision to a human? If that is the thought process which we human goes around, that is the overall thought process when a decision tree works with, right. So, that is where decision tree would actually dominate. So, can I explain the decision to a human, right, and most of the time when we solve a problem, that is the approach that we take. So, it can be a situation can be when the interpretability is non-negotiable, right. There can be number of scenarios where this interpretability is the most important. So, suppose imagine a student asks, why was my admission rejected, right. So, you cannot just answer that the model said so, the model which I have developed said so, right. You have to answer because with reasoning that it was a low entrance score, you got a low entrance score, your incomplete say suppose prerequisites, right, and your weak interview performance led to your non-selection, right. So, that is the thing that I am talking about when the interpretability is non-negotiable and you need to reason, you need to put the reasons behind it. Similarly, like why the decision trees would work is like each rejection follows a clear rule path, right. The admissions committee can defend the decision, and the appeals can be reviewed transparently. So, what is the key over here is when the decisions affect the futures and the explanations are mandatory. So, that is a domain or that is a set of problems where decision tree might work best. Another situation could be when the rules matter more than the raw accuracy, like many systems are not built to be clever obviously. So, they are built to be fair, they are built to be auditable, they are built to show a consistent behavior. For example, in case of tax eligibility, for example, insurance underwriting, it can be the regulatory checks. So, decision trees look like policy manual, behave like flow charts, right. Another thought process could be decision trees do three things which most of the algorithms does not do at the same time. It does decide, it explains and it justifies also. And most of the algorithms which you would study across, which you would come across would not do all these things together. So, when you must explain why a decision was made, in that circumstances probably the decision tree would be a better choice. When the decisions must be defended in front of a humans. So, that is where decision tree would be a better choice. Now, let us take another algorithm which is again pretty important and well known. We call them as a naive Bayes algorithm. So, how do we decide with incomplete information, right? Let us consider a scenario that how do we decide when we do not have a complete information available with us. In real life, there can be many scenarios. We almost never have the complete information most of the time, right? Yet, we humans are able to decide anyway, right? We are able to get a solution based on some kind of thought process called likelihood. So, examples could be, is this email spam? Is this disease likely? Is this news fake, for example? So, naive Bayes would exist because the world is uncertain. Got this point? Because the world is uncertain. So, wherever the uncertainty is there, the naive Bayes could do better. So, let us understand the core idea behind naive Bayes. We start with the belief, right? There has to be some kind of belief in the beginning, right? Then we update with that particular belief with the evidence, right? And then we decide with the confidence, and the naive Bayes does not jump to the conclusions directly. So, it starts with the belief and keeps updating it as the evidence arrives. And this is nothing but you all must have done in your school days as well as in your college days in the beginning. This is nothing but the Bayesian thinking, not just an algorithm, right. So, when you say a doctor never says that you coughed and so you have a disease X, for example, right. Instead, each symptom increases or decreases a belief. If you have fever, then obviously it would raise some kind of probability, right? If normal oxygen is seen, right, it lowers the probability. The test result would update your belief again, and this is exactly what the naive Bayes does and thinks like. Okay. So, when you talk about this word naive, so we call it as a assumption. It is a famous naive assumption. So, it assumes the features act independently even when they do not. In real world, it is not every time that features would be treated as independently or they can be thought as independently, right. So, naive Bayes assumes that the features do not influence each other. For example, the symptoms, the fever, body ache, for example, we have two symptoms, a fever and body ache, for example. So, in reality, they are related, but often both come together obviously, but in naive Bayes, the assumption would be that it would treat both the features separately or independently, it would treat them independently, right. So, how this naive Bayes thinks, let us talk about that concept as well. So, in this case, the fever would increase the disease probability, the example that I took previously. The body ache increases the increases the disease probability. So, even if related, both of them are pushing the belief in the same direction. That is the key aspect over here. So, when the evidence points to the same way, this independence does not hurt you so much, and that is how the strength, and that is why we say that this is a naive assumption, right. So, let us talk about that how actually it thinks. So, for every class, naive Bayes would ask you like how common is this class, how likely is the evidence, and if the class were true, then what we do is we multiply those beliefs, we compare the results, and we pick the strongest belief. That is the entire process of, or that is the entire algorithm, I would say in a very short, that how the naive Bayes actually thinks and works. So, naive Bayes compares the explanations, not the predictions. Remember that it is just comparing those explanations, not at all the predictions part. So, in is today a rainy day or a sunny day, if this is a scenario for example, right. So, what would be the step 1? I am talking about the entire algorithm, right. So, how common is this class, right? We call this as a prior belief, right. So, before seeing anything today, what do we already know? So, something which we know already, we call this as a prior belief, right. Suppose in your city 30% of the days are rainy for example, and 70% of the days could be sunny for example. So, initially the rainy day means less common and the sunny day means suppose more common, and this is the starting belief which I called you as a, which I told you it is nothing but the prior belief. Step 2 could be what? How likely is the evidence? If the class were true, we normally call this as a evidence likelihood, right. So, now you observe some kind of evidence, for example, evidence 1 could be sky is cloudy, right. If today were rainy, so is cloudiness likely? Yes or no could be the answer, right. Is today were sunny, is cloudiness likely? Again you might answer in terms of yes, no or sometimes, right. Evidence 2 could be humidity is high for example. So, is rainy very likely or is sunny very likely? So, each piece of evidence over here supports or weakens your explanation, right. What could be the step 3? In step 3 what we do is we multiply those beliefs, we combine those evidences. So, naive Bayes would stack the evidences together, right. So, rainy explanations started weaker, but evidence fits it very well. Similarly, sunny explanation started stronger, but evidence fits it poorly. So, even though the sunny days are more common in this particular example for the case we took, the today's evidence actually supports rain much more. So, this is how we reach towards, or we are reaching towards a kind of solution. What could be step 4? In the step 4, we simply compare the results. Like now we would compare the two explanations that we gave, right. Rainy days explains what I see better, sunny days struggles to explain the humidity clouds or the cloud, right. And as a step 5, we would pick the strongest belief now. So, the final decision could be today is a rainy day, for example, right. Not because the rain was common, but because the rain explains the evidence better, therefore, we came to a conclusion that the final decision that today is a rainy day. So, if we sum up, the naive Bayes does not ask what will happen, rather it asks which explanation fits better or best, right. So, these naive Bayes algorithms could be more suited where the data is text heavy, right, where we have high dimensions, right, where we have real time decisions to make, right, spam filtering, document classification, we can have the sentiment analysis, right, we would have the news categorization. So, the key idea is when the features are many and sparse, that is where the naive Bayes would be a better choice. And where it would fail? It would fail where the correlated features are there in our data, where the data have complex interactions or the features have complex interactions, right, non-probabilistic logic, for example, right. So, if the problem depends on feature combinations and the order, naive Bayes would always struggle, right. It could be, the example could be the image recognition, right, you could have the complex behavioral modeling. So, this actually this actually helps us to understand that in what circumstances the naive Bayes would be better and what circumstances the decision trees would be better. Now, we will continue with the next session on something called ensemble based algorithms. Thank you for now.